One of the important criteria for simple harmonic motion is that the restoring force and the displacement must always have opposite sign. So if the displacement is a positive displacement, the restoring force must be a negative restoring force. If the displacement is a negative displacement, then restoring force must be a positive restoring force. So what does it mean? Let's study this using a spring mass system. So we have here a spring mass system, then this mass here is oscillating together with the spring. So it's a motion that repeats over and over. So we know that for this kind of oscillation, there must be an equilibrium position, which is the center in between the two maximum. And we have our maximum positive displacement and our maximum negative displacement. So this is a spring mass system. Okay, so now we will look at this spring mass system in two specific moments. We are going to study two specific moments. The first moment is when the object is near the maximum negative displacement. It's near this position where x is equals to negative a. Now we are going to study the displacement and we are going to study the restoring force and see whether they are indeed having opposite signs or not. Okay, so let's look at the displacement first. Okay, we know that displacement must be measured from the equilibrium position. So therefore, the displacement will be measured from x equals to 0 towards the position of the object right now. So we can see that this arrow here is pointing to the left. Therefore, we know that the mass is at the left of the equilibrium position. So if the mass is at the left of the equilibrium position, that means the mass is being displaced to the left. And if displacement is to the left, then that means it's a negative displacement because to the left it's a negative direction. Usually we assume it as a negative direction. So in this case, the x will be negative. Okay, so to be more accurate, is the x component of displacement is negative. Okay, but x component of displacement is represented by the symbol x. So I say x is negative. Or I can say x is less than 0 because less than 0 means negative. Okay, now we have investigated the displacement already. Let's move on to this. Investigate the restoring force. Restoring force is due to the spring. If you compress a spring, there's a restoring force trying to stretch back to the original length. If you have a stretched spring, then the spring will have a restoring force trying to pull itself back to the original length. So that's restoring force. So now you look at the situation over here. You have a compressed spring. The spring is shorter than its original length right now. So if your spring is compressed to the left, then you know that the restoring force will be exerted to the right because the spring will want to come back to its original length. It want to come back to its equilibrium position. So you know the force, the restoring force will be exerted towards the right. And if it's exerted towards the right, then that's a positive direction. So you know that the restoring force here will be positive. Okay, why do I put a subscript x over here? Because technically this is the x component of restoring force. This is the force and the x component of this force over here is positive. Okay, technically there's no y component, but because we want to talk positive negative, right? Positive negative can only be included if it's a component. You cannot include it in f. Because if you just write f only, then that's magnitude. Magnitude must always be positive for a vector. Here we put a subscript x to show that this is the component, the x component of f. And because it's x component of f and it's pointing in the positive direction, therefore the value of the x component of force is positive. Or we can say the x component of f is greater than 0. So now you see, if your displacement is negative, your x component of force is positive. Therefore, they have opposite sign. Okay, let's double confirm our finding with another example. So let's say our object is now on the right hand side of the equilibrium position. So if you can see here, the measurement of our displacement must be coming from the equilibrium position to the position of the object. And as you can see, x is pointing to the right. Therefore, this x here should be positive. The displacement is towards the positive direction. So you can say x is greater than 0, or we can say x is positive. Now, the spring here is definitely stretched. It is longer than its equilibrium position just now. So if it's stretched to the right, then you should expect the restoring force to be exerted towards the left. because the spring you want to revert to its original length, so you want to pull to the left. So you should expect the restoring force to be exerted towards the left, and if our restoring force is towards the left, we know left is the negative direction. So therefore our x component of force should be a negative value because the force is pointing in the negative direction. Or we can say the x component of force is less than 0. Okay, so now we see if the x is positive, then our x component of f is negative. So again, we have checked that they are having opposite signs. So this is the first criteria if you want to check whether something is undergoing simple harmonic motion or not. You check whether the x and the force are having opposite signs or not. Or in other words, you can see that the x and the f must always be pointing in opposite direction. Okay, the displacement and the restoring force must always point in the opposite direction. Therefore, the restoring force and the displacement must always have opposite sign. Criteria 1. Let's move on to the next criteria. Next criteria says that, opposite sign. Next criteria says that restoring force is directly proportional to the displacement from equilibrium. So that means if your displacement is greater, then your restoring force will be greater. So they are directly proportional to each other. Okay, so we know for spring it will approximately obey Hooke's law if the spring does not exceed its maximum stretch. Okay, so we know it obeys Hooke's law. Hooke's law says that the x component of restoring force is equals to negative kx. Okay, k we usually call it spring constant, but in this case we have to be more general. We call it by the name of force constant. Okay, basically it's just a proportionality constant. It's still the same k as the spring constant in Hooke's law. Just that now because k, if it's not the spring, you can still represent it using k also. So it's not specifically for a spring. So we call it force constant. Okay, so fx and x is still the same idea as just now. Okay, so if we look at this equation over here, we can see that fx, the x component of force, and x are indeed proportional actually. Because if it's not proportional, then it will be x squared, or it will be over divide by x. Then fx will be proportional to 1 over x, or fx will be proportional to x squared. Then you can say it's not directly proportional to the displacement. But now fx is proportional to x. Okay, so let's say if this spring over here is having a force constant of 10 Newton per meter. Let's say this spring here has a force constant of 10 Newton per meter. Then if we assign a value for the displacement, let's say over here it's 3 meter, 2 meter, 1 meter, 0 meter, negative 1 meter, negative 2 meter, negative 3 meter. If we know the position or we know the displacement of the object from the equilibrium, then we can determine the x component of restoring force. What we do is just take negative, multiply by 10, multiply by the x that we have over here. Then we will see that our x component of force will have opposite sign to the x. This is criteria 1 that we say just now. If our x is positive, our restoring force will be negative. If our x is negative, our restoring force will be positive. This is the previous criteria that we discussed just now. Now, if you look at this criteria say that they need to be directly proportional. And as you can see, they are directly proportional. If you increase your x, you increase your x component of f. If you increase your x, even though it's in the negative direction, your x component of force will increase as well. So they are directly proportional, and the constant of proportionality is negative k. Okay, this is from your maths. If this is x, then you know it's proportional to x. If this is x squared, then it's proportional to x squared. But now for SHM, it must be proportional to the displacement. It cannot be proportional to the displacement squared. It cannot be inversely proportional to the displacement. It must be directly proportional to the displacement. So you cannot have square over here. You cannot have 1 over x. You cannot have 1 over x squared. So indeed, this case over here, restoring force is directly proportional to displacement. So criteria 2 is achieved. Okay, criteria 3 is on acceleration and displacement. So the acceleration and the displacement must always have opposite sign. So let's check whether that's true or not for this system over here. Okay, so we learned from the previous criteria that this system here obeys Hooke's law. So the x component of force is equals to negative kx. This is Hooke's law. Then we also learned from chapter 4 on forces that sum of F must be equals to ma. And in this case, the object is undergoing acceleration in the x component. So we'll do it in the x dimension only. Okay, so let's check what are the forces acting in the x dimension. And to do that, we need our free body diagram. So let's try to draw a free body diagram for this block over here. And we will draw this free body diagram when the block is over here. Okay, at the maximum compression over here, we'll draw the free body diagram. So we know that this object here has mass, so it has weight. Then this object here is touching this surface, therefore it has normal. So when the block is over here, the spring is compressed to the left. So you should expect the restoring force to be pointing to the right. So therefore, the block will experience a force, will experience a push by the spring, pushing it towards the right. So this force here is the restoring force of a spring. Okay, we know that the normal force and the weight here will be balanced, because if they are not balanced, then the object will start to move upwards or move downwards. But we see that is not the case, so we know that the sum of Fy is 0, this normal and this weight here will be balanced. But for x dimension, we know that this object here is constantly speeding up and slowing down. So we know that it is caused by this restoring force of a spring over here. So the only force acting in the x dimension is the restoring force of a spring. Therefore, we can say that the sum of force in the x dimension is made up of the x component of this restoring force. That's the only force acting in the x dimension. And now we can substitute in negative kx to represent our x component of restoring force. We can substitute max to represent the sum of force in the x dimension. So now if we substitute in, then we know that ma will be equals to negative kx. And now if we shift things around, we will see that the x component of acceleration, also we can just call it acceleration because it's not moving in the y dimension. We say the x component of acceleration is equals to negative k divided by mx. Now, if you look at this situation over here, we can see clearly that this x here is again proportional to the acceleration, because it's not x squared, it's not 1 over x, it's not 1 over x squared, it's x. So again, acceleration is directly proportional to the displacement. And because of this negative sign over here, you know that if your x is positive, your acceleration will be negative. If your x here is negative, your acceleration here will be positive. How do I get this acceleration here? Well, I have my k, I have my m, I assume it to be 2 kg, and if I calculate it, this will be my value over here. And now I've proved using numbers that if my displacement is positive, my acceleration will be negative. If my x is negative, my acceleration will be positive. So the acceleration and the displacement again have opposite sign, and because it has opposite sign, therefore you know that this achieves the criteria for simple harmonic motion. So if your periodic motion here has restoring force and displacement that are opposite sign, and the restoring force is directly proportional to the displacement, and the acceleration and displacement have opposite sign, if all three criteria are achieved, then you know that this system here is indeed a simple harmonic motion. So it's a periodic motion, but it is also a simple harmonic motion. And now I've proved it using some numbers over here to prove that this spring mass system is indeed a simple harmonic motion. Okay, so we are done talking about the criteria you need to achieve in order to make sure something is a simple harmonic motion. Next, you move on to study the displacement, the velocity, and the acceleration, and how it changes with time for a simple harmonic motion.